So good day to all again. We are back here with the lectures on vector algebra. So in the last class we have just seen what is the difference between a scalar and a vector, and then we have seen how to represent a vector with respect to a two-dimensional coordinate system. And now we will go on to a three-dimensional coordinate system and the representation of the vectors. So in a three-dimensional coordinate system, which you are acquainted with from your previous knowledge, we have three rectangular axes x, y and z. The three rectangular axes actually divides our three-dimensional space into 8 portions called 8 octants, and this is here shown both in our figures 1 and 2. Now vectors. So here in the figure 1, let us see first. So here we have a vector OP, which is denoted by R. Now what is O? O is of course the origin of our coordinate system, so its coordinates are 0, 0, 0, and the point P is having coordinates x, y and z. So we see that we have represented our vector with a directed line segment starting at O. Initial point is O and ending at P. So now we have a new terminology also, that this vector OP is called the position vector of the point P with respect to the origin O. So as if this vector O is specifying the position of the point P with respect to the origin. Okay, and now if we come to figure 2, we have again 3 position vectors. I hope everybody can identify here OA, or just denoted by A, OB and OC. These are 3 position vectors with respect to our three-dimensional rectangular Cartesian coordinate system. Now next we will see some very important terms with respect to this three-dimensional coordinate system. They are direction cosines and direction ratios. Let us understand them well, because three-dimensional coordinate system things are already a little bit complicated, and we will see their use or applications in some later lectures when we will advance with this course a little bit more. But now let us understand what are the things. So let us again take a three-dimensional coordinate system, and again OP is your position vector of the point P with respect to O, again denoted as R. Now one thing, the point P is having the coordinates x, y, z. What does that mean? That means the point P is at a distance x along the x-axis. So let us suppose this OA is x, the y coordinate is small y, so let us suppose this is your small y OB, and the z coordinate is small z, this is OC. And now we see here these angles alpha, beta, gamma. What are they? Look carefully that this angle alpha is the angle which our position vector OP is making with the positive direction of the x-axis. Similarly, beta is the angle which OP makes with the positive direction of the y-axis, and gamma is the angle which again the position vector makes with the z-axis. This alpha, beta, gamma, the angles should be of prime importance now, and these angles are called the direction angles. And cosine of these angles alpha, beta, gamma, that is cos alpha, cos beta, cos gamma, these are now called the direction cosines of the vector OP or vector R, which are usually denoted by L, M and n. Now we will try to see the relationship between these direction cosines. Now for that we will once again go back to the previous slide in the previous figure and observe once again little bit here in the triangle OAP. So the triangle OAP, of course this is our angle alpha, this angle POA, this was our angle alpha. OP, this is the position vector r, and if we just take the length, I can say that this OP is having a length r. OA, this is the length x, because the x coordinate of our point P is x. So therefore that means that the point P is at a distance x along the x axis from the origin. So if we just for a minute close our eyes and think carefully, we can understand that this angle OAP, this is going to be a right angle. Although because this is a three-dimensional figure, it's not observable directly, but if we think carefully, then this is going to be a right angle, and that is what we have seen here, because the point P, if we think carefully, once again I repeat, you see that the point P is just overhead of the point A, because this is the distance x and the point P, the x coordinate is x. So this is just overhead of the point A, and therefore the angle at the point A is a right angle, and hence the angle OAP, the triangle, is a right angled triangle. So now from this observation that OAP is a right angled triangle, we get a very interesting relation. See that x by r, what is x? The base of this right angled triangle, and r is the hypotenuse. So x by r, that is the base by hypotenuse. What is that? If we just recollect our knowledge from trigonometry, then x by r is equal to cos alpha, and that is what we have denoted by L. And now y by r, very similarly we can understand, y by r is going to be cos beta or m, and z by r is going to be cos gamma or n. So now see, we get a very interesting relationship, L square plus m square plus n square. What is that? X by r whole square plus y by r whole square plus z by r whole square. So x square plus y square plus z square divided by r square. And what is this? If we think carefully, r is the distance from O to P, so that is nothing but x square plus y square plus z square, r square. So therefore this is equal to 1. So that means we get a very important relation, that the sum of the squares of the direction cosines is equal to 1. And the next thing, direction ratios, this numbers LR, MR, NR. We can see here LR, that is nothing but x, basically the x component, MR is the y component, and NR is the z component. These are of course proportional to this direction cosines. So these are called the direction ratios of the vector r and are usually denoted by ABC. Now, although L square plus m square plus n square is equal to 1, it's very much obvious from these relations that in general we will not get a square plus b square plus c square equal to 1. So in general we can state that a square plus b square plus c square is not equal to 1. Can we say when a square plus b square plus c square will be 1? Can it happen somewhere? Think over that. So this is what I wanted to say regarding the three-dimensional representation of vectors and these important terms as direction cosines and direction ratios. We will need these terms little later at the end of the lecture, when we will proceed little bit with the syllabus in the interior. So with this only we will close today's session, and in the next session we will start with some definitions of some basic terms regarding vectors, and some special types of vectors also. Okay, so thank you, have a good day.